Good afternoon, everyone. I said, all right, well, just gonna settle in, wait for everyone to join in, start soon. So, sit back, relax, grab some water. And yeah, guess we'll do the last chapter tutorial today, and we only have a class on Friday, next Friday. And that'll be it. Just gonna pull up the outline. Enter photo, assignment 1. Well, it's 2 p.m. So hey, let's begin. So hey, everyone, how are we doing today?
Hearing you?
Oh, I'm good. Right. At least Asif and Sarah are doing good. Karim too. 3 thumbs up. Doing well so far. Well, yeah, here we are. Last chapter tutorial. Yeah, so for this chapter, we only really got time to cover the first 4 sections. And what I really want to focus on is the stuff about radioactivity and binding energy. So, okay, Karen, you had a question?
Sir?
Yes.
Yes, I did. For next Friday, do we have class or not? Because of the exit exam for English, some people have. A lot of things have moved from Friday next week to this week, so I want to know if our class is still there.
Oh, you have a Friday, that's right. Well, let me see. You're right. Next Friday is do you know when's the exit exam occurring? That's the English exam, right?
Yes.
Okay, how many people in this class are taking it? Maybe like raise your hand or a thumbs up or something, just so I know if you'll be writing the exit exam. Anyone?
I think the exit exam is only for students in English 3 right now.
Yeah, okay. Well, yeah, as far as I know, we're told by the school not to obviously make you, do any homework on the 21st, but my plan is to, yeah, have a review lecture on the 21st so that we can do some questions together and talk about the, material from over the year.
I'm just thinking, is the Zoom link going to be there or not? That's
Oh, okay. That's a good point. Whether it is or not, I'll keep that in mind. If it isn't, I'll do what Eli's been doing for the labs and just make like a Google Meets or something. Another way, I'll make sure to record the meeting as well, so that it'll be saved. But I do want to take up all the time we have for the Friday class, so it'll be from 12:30 to 3:30 on the 21st. And yeah, so because of Friday, it's going to be a review. I'll maybe go through the old slides, point out a few key things, and do some questions. If there's any questions you want me to work on Friday, you can send them to me. And I already put up some practice questions. I'm going to put up some more, and I'll want to write these solutions for them too. So topics for the exam. I'm still working on the exam. I apologize for taking so long to work on that. I'll finalize my plan today as soon as possible. And from there, I can give you like an official list of topics. Just to kind of give a teaser, you know how you had to draw like standing waves in the first exam? Well, you should still know how to draw standing waves. Like, what do the first couple of harmonics look like? You know, one looks like an eyebrow, one looks like a peak and a trough, one looks like three little things. You should know how to keep drawing harmonics and what the formula for each one is. And you should know what a pendulum is. You should know what a Doppler effect is. You should, what was I gonna say? Yeah, so I'll put stuff up for the relativity as well. That's going to be important to know. You want to know length contraction, time dilation, simultaneity. You want to know speeds as well. So I'll put some questions related to that. You also want to know about relativity and quantum mechanics. You want to know what classical physics kind of couldn't explain and why, you know, relativity and quantum mechanics had to come in to explain stuff. But you should also know in what situations it's still okay to use classical physics. For example, when things are moving at non-relativistic speeds, relative mechanics and classical mechanics agree. So that would be a reason to use classical physics to this day. And right, so yeah, I'll promise you, like today, I know I've been promising for a while, but like I really when I do finalize things today with regards to the final, so you know for sure what's going to be on. So chapter 39 for sure. I think I did it last time, but like I'm not. When it comes to optics, I'll just pull up the outline to show you what I mean. Looking at the optics chapter, because I'm pretty much asked you a lot of questions in the second midterm to do with the gradings. So I'm thinking for the optics stuff, because you did so many diffraction questions, I'm not going to ask anything related to, you know, the double slit experiment or diffraction grading, or you know, just diffraction patterns in general, interference patterns. But I'm still gonna have a question or two, you know, talking about mirrors, reflection, diffraction, and there's definitely going to be a thin film interference question for sure, but nothing to do with the slits or diffraction. I think we've done enough of that. But like I said, I'll finalize the list of topics and post it officially. But like the more nuanced topics, like nothing really nuanced is gonna show up. So like for like say like image formation, where we can just kind of forget about like everything that's not a flat lens or a mirror. But again, I'll finalize that. What's I gonna say? What do you think? I had one more thought. Let's see. Oh, yes. Remember how in the first assignment, I gave you a formula, I think for a particle in harmonic motion, you had a drawing of its position versus time, and you were asked to find information about the position and velocity of it. So you had to look at a graph of simple harmonic motion and figure out stuff like wavelength and period and all that. You should be able to do that. So there are some practice questions put up during the time of the first midterm that had you looking at the pictures and figuring out stuff about the wave. So that's like my big hint here, like know how to do this kind of question, like question 4 in your assignment. And yeah, so today we're just gonna talk about radioactivity. Chapter 44 overlaps greatly with chemistry, so I wasn't, too sad to have to cut it for time. But still, where's my slides? Here we go. Okay. Okay, so this book obviously going to be one question where I ask you to write deal with radioactive decay and probably binding energy, kind of like a 2-for-1. So yeah, I'm not expecting you to memorize the atomic mass numbers. It's something will be given to you. But you should be somewhat comfortable with the idea that a proton and a neutron have an atomic mass of around 1. So you can kind of mental math your way, like you should be able to have an idea of how much an atom or an element should weigh based on the fact that its constituents are 1 U each. Yeah, the atomic radius, the formula here, and that's something you have to memorize, but just keep in mind that the general idea of the nuclei is that it tends to pack itself into a sphere no matter what. So that's why the radius scales with the mass number A, since essentially as you keep adding more neutrons and protons, it just becomes a bigger sphere. In fact, in this sort of model where this nucleus has a spherical shape, the volume is directly proportional to the mass number A. Don't get mass number confused with neutron number and atomic number. Atomic number is kind of confusing because it refers to the number of protons. And yeah, binding energy. So you should be able to apply this formula. What it's saying is that when a nucleus forms, the combined states of all its nucleons is much lower than their total energy when separate. So when a nucleus forming is an exothermic process. When the neutrons and protons bind together, they release energy. In the same way that you need to apply energy to get an electron out of the ground state and ionize an atom, you need to apply much more energy to pry a nucleus apart. So the binding energy tells you how much energy you need to apply to break apart a nucleus. And yeah, carbon-12 is a good example where the atomic mass unit is actually defined so that carbon-12 weighs 12 U. But if you look at the 6 protons, 6 neutrons separately, they weigh a little bit more than that. And yeah, so all atoms, all elements have a positive nuclear binding energy, since again, the nucleus is more stable than the particles separately. And interestingly enough, there's a sort of plateauing of binding energy once you get past nickel. So nickel is the most stable nucleus. That's why it takes the most energy to break it apart. And to create heavier elements, you actually need to add more energy to achieve them, to get them. That's why the more naturally occurring elements on Earth are the ones that have, they're like up to around nickel because they can be produced by fission exothermically. They don't need any extra energy input to produce their next element in the line. But once you get germanium and beyond, you need extra energy, which only comes from stuff like supernova, so that heavier elements can be produced. Anyways, the decay of elements happens randomly, and not all elements do that. Some elements have, a nice number of protons and neutrons that are happily held together by the nuclear force, but some other elements aren't stable. The nuclear force is not big enough to glue the atom together for long. The Coulomb repulsion makes the nucleus want to stabilize itself. And depending on the type of radioactive element, it can do so in many ways. So for example, cobalt likes to emit beta particles and become nickel. And in doing so, it becomes more stable. But the cobalt atom, decays into nickel. So a sample of cobalt-60 over time becomes nickel. The rate at which an element decays is determined by their decay constant. So despite being a random process, on average, you can expect that, once a certain amount of time has passed, one atom will decay, depending on the element. If you're radium, on average, atom of radium can decay in an average of 1 minute, while uranium, takes years for a single atom on average to decay. That's why uranium is so hard to get rid of, because stays around forever. And you can then actually model the amount you have of a sample over time because its decay is exponential. So if you know how much you have, the rate of decay, then you can figure out how much you'll have at a later time. You can also find the decay rate, which the more of a sample you have, the more decays will happen per second or per minute or whatever. But as your sample decreases in size, then on average, less decays are occurring. Very important fact is the fact that because of the exponential decrease in your sample, once your sample has decreased by half, it takes the same amount of time to decrease to a quarter of what it originally was. And it will take the same amount of time to decrease to 1/8 and so on. So the amount of time that takes is called the half-life, which is simply how long it takes on average for a sample to decay to half of what it originally was. So it's not that the atoms are like destroyed completely, but rather they decay into some other element. So the original element is gone from the sample. There's less of the original element left. And again, the half-life is not saying that necessarily, if you're like cobalt that has a half-life of 5 years or so, it's not saying that for 5 years, a sample of cobalt will always lose half of what it was, but on average, it will. So it's more of an average than a hard time limit for half the sample to decay. But for the intents and purposes of calculations, doesn't really affect much. So if you know the decay rate, you can calculate the half-life and vice versa. They're inversely proportional to one another, which makes sense because the faster things decay, the less time it takes for half of the sample to decay. The official unit for the decay rate is the becquerel, named after Henri Becquerel, a French radiologist. Actually, the very first radiologist, when you think about it. And if you're a radiologist of the modern day, you might want to use the Curie unit to define, to talk about decay rates, even though 1 Curie is a lot of decays per second, which is why most elements actually have a couple of micro millicuries of decay. So yeah, it's kind of what you did in the lab, where you see how once you have an initial sample, every half-life, that amount drops by half. So it's kind of like a game of inches. And there's a tricky way to figure out how much of a sample you have left by simply taking the original amount of the sample. And if you know how much time has passed in terms of how many half-lives have occurred, even if it's like a half-life or whatever, then you can find out how much you have left by using this formula here. So it's the original sample divided by 2, and by like divided by 2 for however many half-lives have passed, right? So this is a fast formula that's a bit quicker to use than the exponential one. Again, this is obviously a formula, probably keep you on the final. So, but just just gonna have an idea for at least the decay rate formula and the nuclear amount formula. Have an idea for the fact that they're exponential decay. So as the time passes, the number should decrease for both N and R. And yeah, so just to give you an idea, like I was saying, stuff like radium or lithium, you might think, oh, wow, their half-life is so short, they're super radioactive. And it's like, yes, but high samples of lithium or krypton don't really exist in nature. So while really radioactive, they'll just destroy themselves in like a short amount of time, nothing to worry about. But stuff like radium and uranium will stick around for so long that they just contaminate the planet and they'll be there forever, basically. Fun fact though is that the theory tells us that there are stable elements and unstable elements. So we've seen the unstable ones, like the ones listed here, they're decaying because the nucleus is unhappy the way it is. We haven't seen stable elements decaying. Like, nobody has seen carbon-12 decay, but theoretically, and this is just a fun fact, theoretically, it could still decay. It's just that its half-life is longer than the life of the universe, so just nobody's seen one yet. But when we talk about radioactive elements, we do really talk about the ones that have an observable, beta, gamma, or alpha radiation. Oh, hey, okay, so we had we're here till 3:30, so it wasn't a big advantage of the time today. I want to show you some stuff about Marie Curie because I think her story is pretty fascinating. But I'll go through the tutorial questions first. So question 1, the radius of a nucleus of a, oh man, I forgot. Does anyone know what element is HO? Literally, I can't think of it. Okay, see, oh wait, I see somebody posted in the chat. Where's the chat window? Oh, nope. Man, that's gonna bug me. HO, holmium. Goodness, it's a rare earth element. Okay, holmium. HO is holmium. There we go, I'm learning a lot. Okay, so you want to find the radius of any element. You can just assume, okay, well, we can use the spherical model of the element, and that's going to be equal to it's proportional to 1/3 the atomic number. So the atomic number, by the way, is always on the left up top. Sorry, it's like besides the element name on top. That's the atomic number, A. You should know that from chemistry. So where are we? Okay, so yeah, that's A. And the radius of a nucleus is constant A0 times A 1/3. And you can do is A is 1.2 times 10 to the negative 15. Meters. So this is should remind you of the Bohr radius, but a bit smaller than that even, because the Bohr radius was between an electron and a proton. This is a lot smaller because the nucleus is pretty compact. And A being the mass number is 165 to the power of 13. So if you use the radius formula, 1.2 10 times to the negative 15, 10 to the negative 15, by the way, 1 femtometer is equal to 10 to the negative 15 meters. So this is actually just 1.2 femtometers. I don't know why I put the X. And then 165, that's around 5.5, I think, if you take the cube root. So you should get a radius of about 6.6 femtometers. And if you're wondering, again, when you talk about any element, like in the case of H0, holmium, the general way you draw an element is mass number on top, element name besides it, and the atomic number below. A is the total number of protons plus the number of neutrons, and the atomic number is, well, number of protons in the nucleus. So that's why a lot of the times they won't show you the atomic number, because you can imply it from the element, right? Because every element has a unique atomic number. So if you look at holmium, you can look it up in the periodic table and find out it has 67 protons. And then from there, you can figure out that, okay, well, it has 67 protons, then it must have 98 neutrons. Anyways, yeah, that would be all. So kind of like I said in the recording, a femtometer is tiny. If you recall, when you measured your the thickness of your hair, the radius of an atom is a quintillion times smaller than your hair. So that's not 5 million, that's 1,000,000 and 5 more zeros. So that's like what? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. That's how many times, that's how much smaller a nucleus is than your hair. Okay, so in this question, we're gonna find the binding energy. So if you want to do it in terms of MeV per nucleon, you have to use the full formula, which already accounts for an MeV conversion. Because energy, right, the SI unit is joules, but if you look at the formula, there's a term that accounts for, the formula is written here so that you can just use the atomic mass in U and automatically convert that to electron volts. And as you can see, I don't even remember the formula myself, which is why I'm just gonna. I think I accidentally hit a button. Okay. So yeah, the binding energy, what's the difference between the mass of the separate atoms, sorry, the separate nucleons versus the mass of the helium nuclei, by which I mean tritium. So using the formula, the first one accounts for how many protons you have. So look at the symbol. This tells you that you have a total of 3 nucleons. you have one proton. So how many neutrons you have? Well, you must have 2 neutrons. So the binding energy must be the mass of 2 protons plus the mass of the mass of 1 proton plus the mass of 2 neutrons. Note that the formula, instead of showing you mass of a proton, they tell you the mass of the hydrogen atom. Same thing. One times the mass of a proton plus 2, the mass of a neutron. And then that's the difference between the mass of the separate nucleons minus the mass of the element. In this case, it's tritium. So, and then yeah, there's a conversion factor as well. 931 times 5 MeV per U. And at this point, even though it's annoying to have to write too many decimal places, it is what sets them apart. So you'll have 1.0078 plus 2 times 1.0087 minus 3.016. And we have one more, 0.5 times 931.5 MeV divided by U. So you can kind of tell already that, right? Like you should always get a positive number out of this. Since all binding energy is positive. Now, yeah, so at this point you pull out a calculator. I'm just gonna look at my notes, so it's not to delay too much, but this should get you about 8.66 MeV total. And if you're looking at the energy per nucleon, that just means the energy divided by the total number of nucleons. So you have 3 nucleons, right? That's the total number. A, which is the mass number, tells you how many nucleons you have. So per nucleon, EV is just 8.66 divided by 3. It should be around 2.8 megaelectronvolts per nucleon. If you're wondering how you can remember what the mass number is versus the neutron number versus the atomic number, the biggest confusion I think is for me is like between mass number and atomic number. I like to think that, like, you know, neutron number is self-explanatory, and also a letter for it is N. How do I not get the mass number confused with the charge number, by which I mean the atomic number? I like to think of the A, which is the mass number, which is, you know, neutrons plus protons. I like to think that the A stands for all, you know, all of the nucleus. And meanwhile, the Z, which is the atomic number. Well, I have no particular way to think of why Z makes me think of protons. It's just gonna remember that A is all neutrons and all protons. So by a process of elimination, the Z must be the atomic number, which is also kind of confusing because the word atomic doesn't hint at the fact that it refers to the number of protons. That's why it's said something's called the charge number, which makes a lot more sense because the only charge in the nucleus is due to the protons. But honestly, I've spent a few months confusing myself between mass number and atomic number and which one's which. So it just kind of takes some effort to kind of remember that. A lot of the times, an element, you know, won't show you the atomic number. If there's any number besides an element, it's always going to be the mass number. Or, you know, when it says carbon 12, for example, the assumption is that the 12 is the mass number, because you can imply the charge number by the fact that it's carbon, right? The fact that it's carbon means that it has 6 protons, otherwise it wouldn't be carbon.
Sure.
Mhm.
And what does the value of MT mean?
MT is the mass of the tritium nucleus.
Okay, thank you.
No worries. So yeah, we're comparing the mass of the tritium nucleus, which is a proton and 2 neutrons, versus the mass of a proton and 2 neutrons separately. And that difference in energy is the fact that when the 2 neutrons in the proton form into tritium, energy is lost. Okay. Find the ratio of binding energy per nucleon for helium to uranium. So what you should have for this is the same thing. The binding energy of helium to the binding energy of uranium. Well, let's find the binding energy of helium first. If you look at the number, again, the top is the mass number, the bottom is the atomic number. So that means you have 2 neutrons and 2 protons for helium. So it's going to be 2 plus the mass of 2 protons plus 2 neutrons minus the mass of the helium nucleus. And you're going to want to multiply that by the factor we talked about, the 931.5 electron volts per U. And then for the binding energy of the uranium, it's still the same formula, right? You have to be a bit more careful now. The atomic number for uranium is 92 always. So it's going to be 92 protons plus about 146 neutrons minus the mass of uranium times the energy conversion factor. And I'll leave this as an exercise, but you can see how at this point we're just plugging in the separate masses to get the binding energies. And I believe that uranium has a binding energy of around 8 mega electron volts per nucleon. The helium is not too far from that, so the answer shouldn't be too wild. So that's why, right, like talk about the binding energy per nucleon rather than the binding energy per the whole element, because that way you can compare. It's better to compare it that way. But yeah, you should end up with the difference in binding energy being about 0.94. So again, it's kind of comparable because it's the binding energy per nucleon. It turns out that, again, most elements on average have more or less the same binding energy per nucleon. And the reason that is because over time, there's like diminishing effects when it comes to forming nuclei, where adding more neutrons doesn't make the nucleus that much more stable, so the binding energy doesn't increase by all that much. So that's why the ratio of binding energies, even though helium and uranium are far apart on the periodic table, their binding energies are still similar. Okay. Now this is more of a long question, but it's talking about cobalt-60, which has a half-life of about 5 years. What it does is it decays through beta decay because it wants to become nickel, which is more stable, and in doing so, it emits energy. And the reason why it emits energy is because in the beta decay, it produces well, nickel and an electron, well, a neutrino, which is basically massless. But overall, the mass of nickel is less than cobalt. So some energy also gets emitted. It's exothermic process. So, but first off, though, we need to find out how long after a new sample arrives will it reduce to 1/3 of its original amount. Recall that in a half-life is how long it takes for you to lose half of your original amount. So to lose 1/3 is a little bit more than a half-life. The answer should be somewhere between 5 and 10 years. If you look at the formula for your amount of radioactive element over time, it's a matter of knowing how much time has passed, which is what you're trying to figure out. But we know that there's a particular time, which that's what you're looking for, you have lost 2/3 of your initial sample. Well, so we're trying to find lambda and T. Lambda is always directly related to your half-life, because if you recall, half-life is equal to ln 2 divided by lambda. So it follows then lambda must be equal to ln 2 divided by the half-life. So what that should get you then should be so you can plug in and find lambda. If you're like me, you can just kind of keep doing the algebra. But that means though that, yeah, there's some point where your sample has dropped by 1/3 and you can then solve for T. So you don't even need to know how much of a sample you have left, because there's a NO term on both sides. But you do have, what is it? It's 1/3 times is equal to E negative lambda T. Okay, so now you have to solve for T basically. So you're gonna want to take the natural logarithm of both sides to get rid of that exponential. So you have ln of 1/3 is equal to the ln cancels out, so you have wait, hang on a sec. It's negative lambda T, so you know what's actually easier math-wise, because right, this is equal to 1/E gamma T, sorry, lambda T. So you can just flip them over first. I have 3 is equal to E lambda T. Now you can take the ln of both sides, much more easier, and that cancels out with the exponential on the right side. So now you have that T is equal to ln of 3, that's just a number, divided by lambda. Lambda is equal to the ln of 2 divided by the half-life, so that's going to be ln 3 divided by ln 2 times the half-life, which is 5.25 years. So ln 3 over ln 2, that's about 1.6 if you plug that in. So 1.6 times 5.25 should give you around 8.3 years. So that's it, you just solve for time. And the answer makes sense, right? Because a half-life is 5 years, so you lose a half of the sample in 5 years, you lose 3/4 in 10 years, so you're going to lose 2/3 somewhere in between. Now, as what the material loses in energy. That's the second part of the question. So to find how much the material loses in energy, we need to compare then the rest energy of cobalt with the rest energy of nickel. And whatever the difference is the energy that gets released in the decay process. So I'm going to pull up a whiteboard and do that here. Okay, so basically, right after all that time has passed, which was about, T8 point, I think it was at 3 years, 2/3 of the cobalt 60 has decayed into nickel 60. And the question is, what is the energy difference, between the two elements? So what you can do then is you can just figure out what the rest energy is, because that is the energy of each element. Basically, you're assuming that they're not like excited or anything, so that their energy basically is just their rest energy. So for cobalt 60, its rest energy would be the mass of the cobalt 60 of a single cobalt 60 atom times c squared. And for nickel 60, same thing, but now you read the mass of nickel. And at this point, you will need to know then what the masses of each element is. It will be something that will be given to you on an exam. But I'm just going to pull them up. So I got the facts written down right here. So you can kind of see that in atomic units, the cobalt is ever so slightly heavier than the nickel. So that mass difference also causes a rest energy difference. And then to find the difference in mass, then you can just literally take one mass but minus the other. So then the energy released when one cobalt 60 nuclei decays is literally the difference in mass energy, in rest energy, I mean. So that's going to be the energy release delta is equal to delta M times c squared. And what you can do is, because right now we have delta M in atomic mass units, c squared is in meters per second, but there's a quicker way to get the energy, because there's a relationship between mega electron volts, atomic mass units, and C, which we can take advantage of, which is that where is it? Which is the fact that one atomic unit is equal to 931.5 mega electron volts divided by the square root of speed of light. So you can use that conversion. So delta M was 0.0030307 U. You you can use this conversion here and make it so that 1U is equal to 931.5 MeV divided by times divided by C squared. And now you have C squared here. But the nice thing about this conversion factor, the 931, is that it has C squared on the bottom. So it does cancel out. And that gives you an energy of about 2.82 MeV per decay. So 2.82 megaelectron volts are emitted per decay of cobalt 60. And if we look at the question though, we're asked to define the material loses what percent of its energy through this decay. So to find the percentage of energy lost, then you can just say, well, E lost would be the change in energy for a single nucleon over the total energy of cobalt 60, which we said that cobalt, the change in energy was 2.82. So and that's just the E of cobalt 60 is just its rest energy, which converted to megaelectron volts is huge. It's about 55,000 megaelectron volts. So this fraction then of how much energy is lost versus the energy of a single cobalt 60 is like 0.00005. So only about 0.005% of the energy lost per decay, per beta decay. That's not much for a single reaction, but if you think about it, if you have like a really large radioactive sample and it all started decaying really quickly because the sample's so large, then a lot of energy will be produced in a short amount of time, despite it being a small fraction of the total energy. Anyways, I really like this question because it combines two things, right? It combines rest energy calculations with decay. So I think this is something like on the level of something I could put on the final, where you're kind of have two parts to it, where you ask to consider two facets of physics in one, where, okay, radioactivity first, then rest energy second. Another way to combine this would be to ask about binding energies as well. So this is a good question. Okay. I'll let you try this one. So we have tritium, which has a half-life of 12.3 years. So you know what that is. T1/2 is 12.3 years. And you're asked to find the disintegration constant in seconds. Disintegration constant is just lambda. So you're given T1/2, you have to find lambda. So, so let's try it, see if you can get it, and then we'll discuss. Okay, I'll give you one more minute. Okay. Okay, well, if you got D, you were correct. So half-life of 12.3 years in seconds is about it's like 3. How many zeros is that? I'm going to come to with my calculator. You know what? I should have said it's scientific mode. That's the fastest way, no? Oh, there we go. That is a half-life in seconds. If you do the conversion right, should get you a lot of seconds. 3.88 times 10 to the 8 seconds. So then lambda is just by the formula ln 2 divided by t1/2 should give you 1.89 times 10 to the negative 9 decays per second. Yeah, that's all. Okay, here's one I want you to try out. You start off with a 10-kilogram sample of tritium, and you know its half-life, so how much will be left after 30 years? I'll give you 2 minutes to figure it out. Well, good water. Oh. I'm just going to start filling out the details. Da, da, da. By the way, you don't have to convert to atoms in a kilogram because the answer is also wants the answer in kilograms anyways. So you can use N. You can use this formula if you want. In like it works. It works for masses. Is what I'm saying. Okay, so yes, I'll talk about it. 30 years is about 2 half-lives and a bit. So you should have less than 2.5 kilograms, but more than 1.25, right? Because after 1 half-life, you have 5 kilograms, and then another half-life, you have 2.5, and then after a third, you'd have 1.25. But you're about in between the second and third half-life, so your answer should be in between that. There's 2 ways to go about this. You can use this formula here and find M, where M naught is 10 kilograms. You have 10 kilograms times E. Lambda is, I guess, ln 2 divided by the half-life. So 12.3 years. And then times 30. So what you should get then is something like 10 kilograms times 0.18 if you plug everything in. So you're left with 1.8 kilograms, which makes sense. Another way to have done this is you could have used the shaky formula where you have NO 1/2 to the power of the number of half times have occurred. You can write this in terms of mass. And what you can do then is find the number of half-lives that have passed, which would be 30 years divided by 12.3. So this is probably some number around 30 divided by 12.3 is, 2.4 half-lives. So if you plug that into here, you will get the same answer, 1.8 kilograms. So yeah, not too bad, eh? Yeah, by the way, so if you got B, you were correct. Okay. How are we doing so far? Maybe give me like a reaction. Let me know. All right, seeing a couple thumbs up. Awesome. That's not too bad, eh? That's the last question we'll do. I also like this question, kind of like a assignment type question. So this one, we should be comfortable doing. And okay, so we got 44 grams of petrified wood. The Rutherford Museum, the Redpath Museum at McGill has in its collection a big log of petrified wood. Trees are scary. Not only have they lived like as long or longer than like turtles, they're like thousands of years old, and some of them have been found petrified for thousands of years, which means that trees were around the time of, I don't want to say the dinosaurs, but they're pretty ancient. So carbon dating is when you look up the remaining carbon in like a skeleton or like some decomposed body or like an old plant or a petrified tree. And based on how much carbon a living version of that would have, you can figure out how long ago it was alive. In other words, you can figure out how long something has been dead for based on how much carbon they have left. In other words, when something is alive, like a tree or a human person, the carbon in our bodies is more or less constant. The body keeps resupplying carbon. But when it dies, the carbon doesn't get resupplied, so the carbon slowly withers away. So for petrified wood, it's been losing carbon over thousands of years. So then you can find out, based on how much a tree has of carbon normally, how much it's lost over how much time, and that much time is how long the tree's been dead for. That's what we mean by carbon dating. It's not when two carbons go and have a nice evening together. It's when you figure out how old something is based on the carbon that's left. That's a terrible joke. Anyways, so we found 44 grams of petrified wood, and we were told that in a single gram petrified wood, in a single gram of freshly cut wood, so not the same thing as petrified wood, this is how much carbon we'd expect to find. So obviously petrified wood, there would be less. In other words, we can then determine how much carbon this wood would have had when it was part of a living tree. In other words, we can find the original amount of carbon for 44 grams of wood, which would be 44 grams times this factor here, that every gram of fresh wood has 10 to the 10 atoms, or nuclei, basically. Per 1 gram. And this would be a number of about like 2.86 times 10 to the 12. 2.86 times 10 to the 12 atoms. But this is fresh wood, so obviously the stratified sample of cut wood has less than that. It's been decaying. And we don't know how much atoms are left right now, but we do know, using like a Geiger counter, we're able to find, that it has 100 decays per minute. So we know its current decay rate, which is 100 decays per minute. And what we really want to find is how long it's been dead for. But to do that, we have to have some understanding of either the original decay rate or the current amount of atoms in the sample. So what we can do is, because we know the current decay rate, we can find the current number of atoms, because there's a relationship between the decay rate and n, which is the decay constant times the current number of atoms. That multiplied together gives you the decay rate. So then the current number of atoms is just the current decay rate divided by the decay constant. If you want to get the decay constant, you just, again, the handy formula that's related to the half-life. And the half-life in this case is 5,730 years. Okay, we have to be careful here, because if we plug this in, we're going to get a decay constant in nucleus per year, but R is in decays per minute. So you're going to have to convert either decays per minute to decays per year, or the other way around, so that the time units can cancel out. So be careful for that. Divided by 5,730. Okay, so the decay constant is about 1.21 decays per year. And thus, that's a lot less decays per second, obviously. So you gotta divide that by 365 for days in a year, and divided by 24 for hours in a day, and then divided by 60 for minutes in a day. You should get about 2.3 times 10 to the negative 10 decays per minute. And the reason why I went in decays per minute is because my current decay rate is in decays per minute. So number I have is 100 decays per minute divided by a decay constant of 2.3 times 10 to the negative 10 decays per minute. Gives me 100 divided by that. Gives me 4.34 times 10 to the negative 11. That's right, 10 to the 11 atoms. Okay. So in fresh wood, 44 grams, I would have had 2.86 times 10 to the 12 atoms. Now I have 4.34 times 10 to 11 atoms in this petrified wood. So it makes sense. We have less now because the carbon's been decaying away. So why did we find this out? Well, now that you know how much you would have started with when the wood was fresh to how much you have now, then you can just you can do this two ways. You can use the formula before to solve for T. You know, and find the time it took to go from this to this amount, or you can also use the cheeky number of half-lives formula to figure that out, which that's what I'm gonna do. If you're wondering how you solve for the number of half-lives, well, first of all, let's isolate that term. We'll have n over no is equal to 1/2 n. We can bring the n down by taking the log of both sides. So we have log n over no. Okay, I'm running out of room here. I'm just going to go do this on the whiteboard. There. Okay, so we have log n over no is equal to n log 1/2. So n is equal to log n over no, again, just doing algebra, divided by log 0.5. And we determine what no and n is, so that's going to get plugged in. So it's going to be log 4.3 times 10 to the 11 atoms, divided by 2.86 times 10 to the 12 atoms. Divided by log of 0.5. And what that gets me is an n of 2.72. And this is the number of half-lives, right? So 2.72 half-lives have passed, basically. That's what it's telling us. So that's 2 whole half-lives and about 70% of a half-life. And to find then the total time that has passed, you can just say, well, 2.72 half-lives have passed, so 2.72 times how long 1 half-life takes should be the total time, and you'd be right. So t times 1/2, which is the half-life, t 1/2, that should give you 2.72 times the duration of 1 half-life, which is 5,730 years. Again, this is we were told the half-life already. This should give you around 15,600 years. So this petrified wood came from a tree that died 15,000 years ago. And that's how you solve for an amount with the carbon dating technique. So yeah, this is a really good question that I really like. So it's something I will probably put on an assignment. So you should be comfortable doing some algebra like this to get decay constants and times and amounts. Anyways, does anyone have any questions about the questions we've done for chapter 44? Let me know. And yeah, that's all the questions I've had. For the rest of the lecture, if there's no further questions, I do want to show you a quick little 5-minute video on Marie Curie, because I think she deserves attention. And well, her husband too. They were kind of like a cool duo of physicists. And I think this lets me share sound. Let me know if you can't hear anything. Let's share the sound. Just in case. I'll capture
If you
on.
want a glimpse of Marie Curie's manuscripts, you'll have to sign a waiver and put on protective gear to shield yourself from radiation contamination. Madame Curie's remains, too, were interred in a lead-lined coffin, keeping the radiation that was the heart of her research, and likely the cause of her death, well contained. Growing up in Warsaw, in Russian-occupied Poland, the young Marie, originally named Maria Skłodowska, was a brilliant student, but she faced some challenging barriers. As a woman, she was barred from pursuing higher education, so, in an act of defiance, Marie enrolled in the Floating University, a secret institution that provided clandestine education to Polish youth. By saving money and working as a governess and tutor, she eventually was able to move to Paris to study at the reputed Sorbonne. There, Marie earned both a physics and mathematics degree, surviving largely on bread and tea and sometimes fainting from near starvation. In Paris, Marie met the physicist Pierre Curie, who shared his lab and his heart with her. But she longed to be back in Poland. Upon her return to Warsaw, though, she found that securing an academic position as a woman remained a challenge. All was not lost. Back in Paris, the lovelorn Pierre was waiting, and the pair quickly married and became a formidable scientific team. Another physicist's work sparked Marie Curie's interest. In 1896, Henri Becquerel discovered that uranium spontaneously emitted a mysterious X-ray-like radiation that could interact with photographic film. Curie soon found that the element thorium emitted similar radiation. Most importantly, the strength of the radiation depended solely on the element's quantity and was not affected by physical or chemical changes. This led her to conclude that radiation was coming from something fundamental within the atoms of each element. The idea was radical and helped to disprove the long-standing model of atoms as indivisible objects. Next, by focusing on a super radioactive ore called pitchblende, the Curies realized that uranium alone couldn't be creating all the radiation. So, were there other radioactive elements that might be responsible? In 1898, they reported 2 new elements: polonium, named for Marie's native Poland, and radium, the Latin word for ray. They also coined the term radioactivity along the way. By 1902, the Curies had extracted 1/10 of a gram of pure radium chloride salt from several tons of pitchblende, an incredible feat at the time. Later that year, Pierre Curie and Henri Becquerel were nominated for the Nobel Prize in Physics, but Marie was overlooked. Pierre took a stand in support of his wife's well-earned recognition. And so both of the Curies and Becquerel shared the 1903 Nobel Prize, making Marie Curie the first female Nobel laureate. Well-funded and well-respected, the Curies were on a roll. But tragedy struck in 1906 when Pierre was crushed by a horse-drawn cart as he crossed a busy intersection. Marie, devastated, immersed herself in her research and took over Pierre's teaching position at the Sorbonne, becoming the school's first female professor. Her solo work was fruitful. In 1911, she won yet another Nobel, this time in chemistry for her earlier discovery of radium and polonium, and her extraction and analysis of pure radium and its compounds. This made her the first, and to this date only, person to win Nobel Prizes in 2 different sciences. Professor Curie put her discoveries to work, changing the landscape of medical research and treatments. She opened mobile radiology units during World War I and investigated radiation's effects on tumors. However, these benefits to humanity may have come at a high personal cost. Curie died in 1934 of a bone marrow disease, which many today think was caused by her radiation exposure. Marie Curie's revolutionary research laid the groundwork for our understanding of physics and chemistry, blazing trails in oncology, technology, medicine, and nuclear physics, to name a few. For good or ill, her discoveries in radiation launched a new era, unearthing some of science's greatest secrets.
Marie Curie is pretty cool. Yeah, a bit of a sad story though about her and her husband. At the time, so little was known about effective radioactivity, which is being studied, but can cause serious harm to the body, of course. I do have one more clip. This one is meant to be comical. The Simpsons has apparently done a joke for every single thing in the existence, including the Curies. So this is a clip from an early Simpsons episode.
Marge, you're making a big mistake. I'm gonna see you all day at work and all night at home. And that's good. But here's the bad part. Oh, look at that headline. Canada to hold referendum. Sorry, Marge, can't talk now.
We need the money, and my life is pretty boring. Last week, some Jehovah's Witnesses came to the door, and I wouldn't let them leave. They snuck away when I went in the kitchen to get more lemonade.
Yeah, lemonade is good.
I think it's wonderful. Mom and Dad, side by side at the power plant. You'll be just like Marie and Pierre Curie.
Well, there you go.
They discovered radium. Then they both died of radiation poisoning.
It's the Curies! We must flee!
Whoa.
Anyways, that's all for today. So yeah, no, I promise you I'll.
Ever since it first came onto air in 1989,
Hang on, why is this still
it's
playing?
set itself apart.
There we go. Yeah, I promise you I'll finalize the stuff for the final, so I can get you a list of topics to focus on, and I will send you some questions related to relativity, as well as some stuff about topics. Yeah, some other stuff as well. Yeah, I'll put up solutions, and otherwise, yeah, we'll see you all one last time on Zoom or whatever Google Meets on Friday. Then we'll see each other in person on the 23rd. And I will have, office hours still Mondays at 7. So I'll put up the most general equations in the formula sheet, which you'll have access to before the exam. But you won't be expected to memorize any general equations. I might still ask you to derive an equation on your own, I don't know, how I asked you to get standing waves in the first midterm, but I won't expect you to memorize any equation. However, any question that's directly a law, I probably won't give you, the law of reflection, the fact that incident angle equals reflected angle, that's something you should know. But most stuff like Snell's law, yeah, I'll give that to you. But yeah, not really. Yeah, I'll give you the equations. I don't want it to be all memorizing equations. There's still gonna be conceptual questions though, so it's worth understanding what each equation tells you, obviously. Anyways, yeah, so you still have office hours on Mondays at 7 if you have any more questions. And yeah, otherwise, it's super sunny outside. It's nice. I'm wearing shorts for the first time in this year, so I think bright sunny days are ahead for all of us. So I'm gonna let you go and enjoy the day. Thank you for coming to this lecture. We'll see you one last time on Friday, and until then, have a good weekend.
Thank you, sir. Have a
Thank
good
you,
day.
sir.
All
Thank
right.
you, sir. Bye.
Bye.